So we said in the last lecture that the bonds are formed from sharing of pairs of electrons. So if you've got X and you got Y and they form a single covalent bond, then we can write a pair of electrons between them, right? Or we can just go ahead and write a line. Now the interesting thing is that that pair of electrons is not always shared perfectly. In fact, we normally assign what we have an electronegativity scale, and the electronegativity, if I can spell and write at the same time, is a number, a scale that ranges from 0 to 4, let's say, and what it tells you is the ability of the atom to draw electrons towards it. So it's the ability of each atom to essentially attract electrons out of the bond. So if an atom has an electronegativity of 4, then it is pretty amazing at pulling electrons. So it's very strong at pulling electrons towards it. And if it's got something like an electronegativity of 0, which I'm not sure if anything goes all the way down to 0, it's basically incredibly weak at pulling electrons out of the bonds. So it is essentially a fight to the death. So let's go ahead and take a simple molecule like hydrogen fluoride. So if we look at hydrogen fluoride has a Lewis structure that looks something like this. We've got a bond here in the middle, and we've got 3 lone pairs around the outside, and the electronegativity of hydrogen is actually 2.1. So hydrogen actually has a very middling electronegativity. Fluorine is 4.0, and that maxes out the scale. So what that tells us is that those electrons in the bond are actually pulled more towards the fluorine and less towards the hydrogen. So it essentially is just a fight, and the electrons are pulled towards the more electronegative atom. And so in this case here, the electrons are kind of pulled towards fluorine, which has a higher electronegativity, and away from hydrogen, which has a lower electronegativity. And so what that means is that the right-hand side of the molecule actually has a slight negative charge. So we're going to write delta minus there. And the left-hand side of the molecule has a slight positive charge because the electrons are pulled away from there. And if you're wondering what the symbol here is, the symbol here is the Greek letter delta. And you might be used to capital delta, that is used for large change. And we use a lowercase delta for small change. There's another way we can represent this too. We can write what we call an electric dipole moment. We can draw an arrow that basically shows the direction the electrons are being pulled in the bond. And so this is an electric dipole moment. So electric because it's an electrostatic charge, a positive or a negative. Dipole because there's 2 ends to it, so there's a positive end and there's a negative end. And you can think of these like the poles on a bar magnet, the north and south, but instead these are the electric poles, the plus and the minus. And moment is actually just a physics word telling us that it's actually a vector, and it actually has magnitude and direction. So in this case here, our vector is pointing to the right. Whenever we have this, we have what we call a situation called a polar bond. So whenever one end of the molecule is positive and one end of the molecule is negative, or I should say one end of the bond is positive and one end is negative, we call it a polar bond because we've got these polar regions, these positive and negative regions in the same bond. So here's a scale of the electronegativities as we look across the periodic table. And I really like this one because the elements that are more electronegative are kind of drawn higher, and the elements that have a lower electronegativity are kind of drawn lower. So I think it really is nice as you go from sort of left to right across the periodic table. Of course, the number of protons in the nucleus increases, so their ability to draw electrons away from another atom in a bond also increases. You can see there that fluorine is the highest one on the whole table here with an electronegativity of 4. We see a couple of trends here. So certainly the first trend is as we go from left to right, the electronegativity, or I'll just write AEN for short, increases. And also notice as we go from the bottom to the top of the table, the electronegativity increases. And I would say that makes sense for 2 things, for 2 reasons. One, as you go from left to right, there's more protons in the nucleus, so the electrons should be more attracted. And of course, as we go to the top of the periodic table, right, as we go up the groups, the sizes of the atoms get smaller and smaller, which means that now the electrons are going to be closer to the nucleus. They're going to experience a much stronger attraction, and that culminates really at fluorine, that sort of top dog here. You'll need to actually memorize some of these, and I would say that the ones you want to memorize come into the first 2 periods of the periodic table. So you've got hydrogen at the very top here, And then you got lithium through fluorine, and I think you should find this easy to memorize because you notice it starts at 1 and it goes in steps of 1/2, so it is very easy to remember. Hydrogen is sort of in between boron and carbon, I suppose. Some periodic tables actually put it up here because it is closer in electronegativity to, say, carbon than it is to lithium. So that's one argument for not putting hydrogen all the way over here. But you really need to know these general trends. And outside of the second period, right in the first period, you just have to know they go up. Maybe not as dramatically. And actually, if you look at the transition metals, they're kind of squirrely. So it goes up, and then goes down, and then goes up, and then goes down, and then goes up again. So this sort of transition metal block region here is where strange things happen. One last little thing here. The bigger the difference in electronegativity, the more polar the bond is. So if we calculate the difference in electronegativity, if we get a difference of 0 to about 0.4, we actually describe the bond as being nonpolar. So we don't consider it to have a sizable positive and negative charge on each end. And just to give you an example of this, so something like chlorine, or something where the electronegativities are almost exactly the same, IBr, or a bond like carbon-hydrogen. These are all examples of nonpolar bonds. In the case of chlorine, of course, it has to be 0, but in the case of carbon-hydrogen, so carbon I think is 2.5, hydrogen is 2.1, so we know that this end will be slightly negative, and this end will be slightly positive, so it'll have a dipole moment that points towards the negative. I always think the pointy end of the arrow, right, is the corresponding to the negative end. Looks something like this, but it is so small in the same way that if I gave you 1 penny a year as a raise, it would be technically a raise, but practically not much of one at all. As we go from a difference of about 0.4 to about 2.0, then we have what we call polar covalent. And so the bigger the difference is, the more polar it is. So for example, something like carbon chlorine or carbon fluorine. So that's a more and more polar bond. So carbon's 2.5, chlorine is 3, and fluorine over here is 4. So the difference in electronegativity for this one is 0.5, and this one here is 1.5. So the electric dipole moment there points to the more electronegative atom. So chlorine in this case and fluorine in this case. Notice I draw the arrow longer, the bigger the difference is. Why is that? Well, the bigger the difference, the more positive, the more negative each end is. And the smaller the difference, kind of the smaller positive and the smaller negative we have here. So think of this as like a really rocking bar magnet, you know, where you've got a large difference versus one of those wimpy bar magnets that kind of barely sticks onto your fridge if the difference is small. Now, what happens if the difference is bigger than 2? So if it's bigger than 2, we actually consider this to be ionic. So case in point, something like sodium chloride. If you take sodium and you take chlorine, sodium's electronegativity is 0.9, chlorine is 3.0, that difference is 2.1. In fact, that is so large, we essentially say the sodium has lost the electron to chlorine. And so now you've got an ionic bond. You've got sodium positive and you've got chloride negative here. So why do we have these hard cutoffs? Well, honestly, we got to pick somewhere for there to be a cutoff. And so I don't think it's worth arguing too much about whether it's 0.4 or 0.3 or 0.5. Some books say 1.7, 1.8, 2.1 for the polar ionic cutoff. I'm not sure it matters too much. Let me just show you one quick chart and then we'll put this to rest. So this is a wonderful graph from our textbook, and it shows the electronegativity difference on one axis versus the percent ionic character on the other axis. So for instance, for chlorine over here, then there's no difference in electronegativity. So clearly it is 100% covalent or 0% ionic. So it would fall right here on our graph. Whereas when we go to something like HCl, the difference in electronegativity is 0.9, and we can see it's somewhere on the order of 25% ionic, 20% ionic, so about 80% covalent. If we look at the electron density right here, we can see there's shared electrons here, so there's some kind of a covalent bond here, but we see the electrons are getting kind of pulled away from this region here. Whereas if we go to something like sodium chloride, whose difference in electronegativity is 2.1, we can say that looks pretty darn ionic. However, we can calculate it. It's a little bit shy of 75% ionic, so there's still a little bit of electron density in this region here, but you can see it's mostly being pulled towards the chlorine and away from the sodium. And I think what this really describes best is that it is a continuum, so it's impossible to say something is purely covalent or purely ionic, and so it's kind of arbitrary where we set the cutoffs at. So I think 0.4, we just say, it's really not much of anything, so at 0.4, really, everything to the left of this line here is essentially non-polar covalent, so pure covalent. And to the right of 0.4 all the way to about 2, right, we're going to say everything in here is going to be polar covalent. So the more electronegative atom is going to be the one that has the negative charge. And then to the far right-hand side over here, right, we're going to say everything over here is essentially going to be ionic. So things like potassium fluoride, right, the electronegativity difference is, golly gosh, what, about 3.2? And we're saying it's about 80-85% ionic. So lithium fluoride is the most ionic compound here on here, and we're getting it about 85 to 90% ionic when the difference is about 3.0. So nothing is black or white, unfortunately, or fortunately, actually. I think it's more interesting. But where we draw the cutoffs is relatively arbitrary, but we have to draw the line somewhere, right?